Hello everyone. I am Krishna Kumar, an early stage researcher in the TERAOPTICS Consortium. I am currently employed at Das Photonics and enrolled for my PhD degree at Polytechnic University of Valencia. I am working under the supervision of Carlos Garcia, a Chief Science Officer at Das Photonics, and Borja Vidal Rodriguez, a professor at Nanotechnology Center of Polytechnic University of Valencia. In this video session, I am going to talk about the applications of terahertz radiation, mostly about terahertz spectroscopy and terahertz imaging that cover most of the terahertz applications. So, as you might have heard in our previous lectures, terahertz radiation have several attractive properties such as non-invasive non-ionizing properties, unique spectral fingerprinting, coherent detection, phase sensitive to polar compounds, and high spatial resolution compatibilities. These attractive properties of terahertz radiation with recent technological advancement in terahertz technology have led to numerous applications in various domains of science, engineering, astronomy, and medicine. For example, terahertz radiation have much less energy than optical rays and X-rays, so less that it can barely ionize biomolecules or can hardly produce any kind of thermal effects. These specific properties of terahertz radiation make it suitable for medical applications where real-time diagnosis, regular monitoring, and screening of patients is required without producing any significant side effects. Similarly, a strong absorption of terahertz radiation by water molecules further allow terahertz radiation to identify tissues with different water level concentration, and that basically help in detection of cancerous tumor cells. Besides all this terahertz application, terahertz radiation can also penetrate a wide variety of non-conducting materials like plastic, wood, ceramic, paper, paint, cardboard, and various other without damaging them. Since the penetration is limited to thin materials, it is useful for material characterization, layer inspection, relief measurement, and producing high-resolution images. It is also possible to recreate some of the tissues and some of the organs in 2D or 3 dimensions to access its internal characteristics. For example, we can use terahertz tomography and terahertz holography to see all those organs. Another silent feature of terahertz radiation is coherent detection that allow us to measure the refractive index and absorption coefficient of active terahertz samples. For example, a strong absorption peak present at terahertz frequency in explosive like RDX help in detecting explosives hidden under clothing, paper, plastic, etc. There are many other applications of terahertz radiation which is currently functional, and several possibilities are being further explored using terahertz spectroscopy and terahertz imaging. Similarly, we can have terahertz endoscopy and terahertz tomographic techniques to have all this to cover all the other applications. Here I will explain about the terahertz spectroscopy and terahertz imaging. So the question is, why terahertz spectroscopy? Well, spectroscopy is a method to study the interaction between electromagnetic radiation and matter as a function of frequency or wavelength. Depending on the frequency of the radiation, we can have a wide range of spectroscopic techniques. For example, if we use a UV visible light, we can have UV visible spectroscopy. Similarly, we can have infrared spectroscopy, nuclear magnetic resonance spectroscopy, and we can have terahertz spectroscopy, where we can use terahertz radiation to identify active terahertz molecules by targeting their molecular vibrations. Molecular vibrations such as rotational, torsional, crystalline phonon, intra and intermolecular transitions. In addition to all this, small alterations in their structure or concentration can also be studied with terahertz radiation. Apart from that, terahertz radiation can provide time domain analysis of vibrational mode on sub-picosecond or picosecond levels. And it can also provide a spatial resolution of micrometers by using near field spectroscopic techniques. So let's talk about terahertz time domain spectroscopy. Terahertz time domain spectroscopy have another advantage over optical spectroscopy, where direct measurement of electric field is not possible in optical region. There are multiple techniques such as electro-optics sampling and antennas allow us to directly measure the time evolution of terahertz radiation from the sample. Let's split this whole process in 3 steps to understand it easily, where the first part is terahertz generation, the second part is terahertz interaction, and the third part is terahertz detection. So as you can see, laser pulses from this titanium sapphire femtosecond laser is first guided towards a beam splitter that splits the beam in, let's say, assume 90-10 ratio. The 90% of the beam, so also called pump beam, is guided towards photoconductive antenna for terahertz generation, and 10% of the beam is used as a probe beam for the signal detection. So as you can see here, it goes to the electro-optic crystal. The generated terahertz radiation is then allowed to pass through a sample that is kept on a 3D translational stage, and the signal from the sample is then collected on an electro-optic crystal for electro-optic sampling. The probe beam is guided through a delay stage and a set of mirrors to match the path length of pump beam and the probe beam. The pump beam and the probe beam are guided towards a balance detector through a quarter wave plate and a Woolston prism. The main part of terahertz time domain spectroscopy is terahertz detection, where directly the electric field is measured in time domain rather than measuring the intensity. Since the terahertz transmitted signal from the sample has very short lifetime of picoseconds, and due to unavailability of optical detector with picosecond resolution, we use electro-optic sampling technique to retrieve the signal in sub-picosecond resolution. And this is done by adjusting the relative distance between the two femtosecond laser pulses at the electro-optic crystal using a delay line. By adjusting the delay, the signal is sampled with femtosecond resolution, and the spectral information of these time traces signal are extracted using fast Fourier transform analysis. Now, by comparing the delay in the pulses when when we had the sample and when we don't have the sample, we can extract the refractive index of that sample. Whereas by comparing their intensity and the phase profile, we can extract the absorption by that sample. Also, by looking at the absorption spectrum, we can identify the samples such as explosives like RDX. Now, let's focus on terahertz imaging. The first ever terahertz image was generated long back in 1960. Since then, with the help of technological advances, terahertz imaging find applications in several domains of science, engineering, astronomy, and medicine. For example, researchers from A&T Bell Laboratories recorded an image of a packaged electronic chip for the first time in 1995. In 2002, the Tiger team of European Star Agency produced the first passive terahertz image of a hand. In 2004, a True Vision Limited successfully captured the image of guns and explosive underclothing with world first compact terahertz camera. Since then, numerous applications of terahertz imaging have already been demonstrated and are being further investigated. In this session, I am going to explain the basics of terahertz imaging. Following this video, you can also record terahertz image in transmission or in reflection mode. Now, let's understand the process of terahertz imaging, taking examples of two samples. This is the basic terahertz imaging setup, which is used for imaging these two different samples. The first sample is silicon lips on gold substrate, and the second sample is gold lips on silicon substrate. As you can see, gold reflects the terahertz radiation and silicon transmit the terahertz radiation. We use these characteristics of terahertz transmission and terahertz reflection to image these two samples using this terahertz imaging setup. As you can see, terahertz radiation of frequency 0.6 terahertz from this terahertz source is first collimated and then focused onto a sample with the help of mirrors. The transmitted signal from this sample is guided towards detector D1 with the help of two parabolic mirrors that collects the transmitted signal from the sample and then focuses it onto detector D1. Similarly, reflected signal from the sample is guided towards detector D2 with the help of two mirrors, PM1 and PM4, and the beam splitter BS. A sample placed on a 3D translational stage generally moves the sample in the focal plane of this parabolic mirror. This way, we can record the terahertz image of these two samples in both transmission mode and reflection mode. Now, let's look at the recorded terahertz transmission images. As you can see here, we have two images of completely opposite contrast, where one have bright lips and the other have dark lips. When focused terahertz radiation strikes the gold part of the samples, most of the radiation gets reflected towards detector D2, and the only radiation that strikes the silicon portion in these two cases reaches detector D1. This way, in the case of sample silicon lips on gold substrate, we have bright lips on dark substrate in transmission mode, and for gold lips on silicon substrate, we have dark lips on bright substrate. Also, due to the lower terahertz power, it is really important to place the sample exactly at the focus and align the sample in the focal plane to obtain really accurate images. However, if you have noticed, not all the silicon lips on the gold substrate are perfect, and we have some fabrication defects that we can also identify in its terahertz image. And this way, we can find defects in the samples, whether it is covered with plastic, paper, cardboard, and several other terahertz transparent materials. This way, we can find applications of terahertz imaging and terahertz spectroscopy and several other applications. Thank you for listening. I hope you enjoyed our lectures.